In this video, we're going to revisit some of the properties about a median of a triangle. So first, we should remind ourselves that a median is when the vertex of one corner of the triangle is connected to the opposite side's midpoint. So if each side of a triangle has a midpoint, the midpoint is going to be drawn in and connected to the opposite vertex. That means we're forming a median. So in these three pictures here, we're going to connect them. So what I mean here is if we have a vertex, when I connect it to the opposite side's midpoint, this is a median. Okay? Just like here, connect to the opposite side, we get a median, and vertex to the opposite side's midpoint, we get a median. Okay, same thing in the next one. We have a median here, another median, and one more median. And last triangle here, from a vertex to the opposite side's midpoint, vertex to the opposite side's midpoint, and vertex to the opposite side's midpoint. We're here. Now, one thing that's true about this is that each of these medians intersect, they all meet inside the triangle. Okay, so what's true about the medians of the triangle? They intersect inside the triangle. Okay, and with that being said, when they intersect inside the triangle, that intersection point's known as the centroid. Okay, so it's been a while, but that point of intersection is the centroid. Now, we dealt with that all through the points of concurrency when we first started doing constructions back in Unit 4. But so each of those points, that's known as a centroid. The fact that the three medians of a triangle all intersect at the same point is known as the concurrence of the medians. Okay, the three angle bisectors and three perpendicular bisectors also have their own points of concurrency. We've dealt with all of those at one point, but the one we really care about today is the centroid. So when I look here at exercise 2, in the triangle below, we have the midpoints D and E of sides A and B have been connected to the vertices B and C to form those medians. What are two ways that DE and BC are related? So remember, when we have midpoint here, those two pieces are congruent because we know D and E are the midpoints. But this line, DE, is known as the midsegment because it's connected to two midpoints. That line, DE, is always going to be 1/2 of the third side of the triangle. So it's going to be half of BC. And DE is parallel to BC. Okay, that's because the midsegment's always parallel to the third side, so the side that doesn't have a midpoint drawn to it, and it's always going to be half the length. So that being said, since I have parallel lines, when I'm looking here, we're trying to show why DEF, this triangle here, and CBF here are similar. Well, there's a couple of different things we could go about saying and doing, but since we just shown that they're parallel, we have two pairs of congruent alternate interior angles. So parallel lines form congruent alternate interior angles. Triangle DEF is similar to triangle CBF by angle. So now last piece, when we're trying to make this proof for this last part to all come together here, we're trying to prove that BF is equal to twice the sides of FE, and CF is equal to 2 times the size of FD. Well, what we have to know here is that similar triangles all have proportional sides. So if I'm making a formal proof, because now says the word proof, and you could just explain it and it would get away with it here, but if I was to do a formal proof in this case, I know we've already done enough to show that triangle DEF is similar to triangle CBF. So I'm going to say that's my given because we already shown that. Now remember, all the sides are in proportion. So corresponding sides of similar triangles are proportional. But so let's actually set up those proportions. So I'm going to take the proportion that I have. I know here that DE and BC were related. So if I look at where DC and then if I look at this other side, DE is here. BC is the bottom piece. The other one that's on the smaller triangle with that is EF. So we'd have EF and BF. Likewise, I could say DE over BC is equal to, again, we want the smaller piece, so I can also say that FD is over CF. So we know they're in that proportion here. So I could go through cross multiplying, but it's not asking me for the product of the means. Instead, what I know is we also already shown that D is equal to 1/2 BC. Now that's just the same as having BC is equal to 2 times DE. So I know that already. Oops, fix that to BC. So since those sides are proportion, I could just finish this off here that BF is equal to 2 of FE and CF is equal to 2 of FD because sides are in proportion. Since I just said the sides are proportional, since BC is equal to 2 DE, all sides in similar triangles are proportional. So if we know one scale factor, we know them all because all three of them should follow the same amount. Okay. Now, that means that the three medians of a triangle concurrently intersect at the same point and divide a segment into a 2-to-1 ratio. So when I connected the medians down here, a median is saying that this side right here was twice the size of this little piece. This piece was twice the size of this piece, and this piece was twice the size of this piece. So that's going to be true every time we have medians. So that being said, if JH is 8, FG, this entire thing, is 18, we're going to find the other lengths. So along this piece DH, it's in a 2-to-1 ratio. So I could say like that's 2x and x. So 2x to x, if this one's 8, I'm going to double that, and the length of DJ will be 16. When I look to find DH is just saying the whole thing now. So I'm taking 16 plus 8 and getting 24. And the last one, FJ, when you want to find FJ, if the whole thing is 18, it's in a 2-to-1 ratio. So I'm going to say 2x and x, because that one piece is 2 times the size of it. So 2x plus x equals 18. 3x equals 18. X is equal to 6. Now x is the smaller part. Since we want FJ, I'm going to go in and times that by 2. So we'll get 12. So it's always a 2-to-1 ratio anytime you have those medians that intersect. So we talked about that point being called as the centroid. So you could be able to construct a centroid, and we spend a lot of time doing that in Unit 4. Okay. So first we have to remind ourselves how to do the midpoint. So go ahead and pause the video for a second, because I believe most of us should remember how to make this construction. But go ahead and pause the video and make that construction. Each endpoint, you should have started from A and made an arc that's more than halfway, so that extended from both sides. Then without changing the size of that arc, you would have moved your compass to B and done it again and drawn the line. When we do that, we should end up with something that looks like this, where at this point here in between, that's going to be my midpoint right here. Okay. Now, that same strategy is how we find the centroid, which we've done before in Unit 4. So what we would do here is find where all 3 medians of the triangle intersect. So I want you to take the midpoint, do that same perpendicular bisection construction of BC, then repeat it from AC, and one more time from AB. And when you have all 3 of them, then you can find where that point intersects. So pause the video and make those 3 constructions from each of the 3 lines. So you're going to see on the other page, I have drawn in 3 different perpendicular bisectors. So I found the midpoint of each piece, but be careful, because the midpoint isn't necessarily the median, because that's not, I don't want where these 3 meet. That's the one thing you want to be careful about in this case. I'm just going to move this one over a little bit. So remember, to finish this off, the 3 medians, one of them is from the vertex to the opposite side's midpoint. So it's going to be here to that blue line about. I'm going to move that, get it a little bit straighter in there. So there's one of them. The other one is the vertex to the opposite side's midpoint, so to the green. And the last one will be the vertex to the opposite side's midpoint. And you'll see that they all intersect at that point here.